All right, here's the last thing that we're going to do in chapter 14. This is calculating the pH of salts. And you're saying, what the heck's a salt? And whenever I say salt, everyone always thinks of this stuff, NaCl. So the question we're asking is, when we put a salt in solution and it dissociates, will either of these products have any acidic or basic properties? Well, obviously, sodium's not going to have anything. So this one doesn't affect pH. What about this other stuff? Cl minus. What do we know about that? Well, we know that Cl minus is the conjugate base of HCl. That means it's going to act like a base. So we could calculate the pH. The only problem is that HCl is a strong acid. And the conjugate base of a strong acid like HCl is too weak to affect pH. But what if it was a conjugate base of a weak acid? Because the conjugate base of an acid that doesn't dissociate very much is going to be stronger. So here's an example of a salt. And a salt is simply any positive and negative ion. So here's another example. This is a salt, KCN, because it dissociates into K plus and Cn minus. If you're wondering where I got this from, it's on your list of polyatomic ions. Now, something like this doesn't affect pH, but this does. Now, how do we know what this is going to do in solution? We know that this is the conjugate base of an acid, of HCN. How do I know? Because I have a table, and here it is right here. It's called hydrocyanic acid. It has a Ka, 6.2 times 10 to the minus 10th. So here's the deal. When we have the conjugate base of HCN, this acts like a base with a Kb that is going to be equal to Kw divided by Ka. You're saying, what? Here's what we're saying. If we know that a base is any solution that produces OH minus, you could find the concentration of OH minus simply by dividing it by the concentration of H plus. Well, where do we get this stuff from? Here and here. So if we want to find the Kb of a conjugate base, that is the conjugate of a weak acid, we could simply say Kb is equal to Kw over Ka. So if we wanted to find the Kb for this hydrocyanic acid, for this conjugate base, Cn minus, we'd plug it right in here. We'd say Kw is always 1 times 10 to the minus 14th. And what did we say was the Ka for hydrocyanic acid? All you got to do is plug this in. This tells us the Kb. And once we have the Kb, we can find the pH. So 6.2 times 10 to the minus 10th. What's our Kb? Let's take out our calculator, and we'll say 1 times 10 to the minus 10th. I'm sorry, times 10 to the minus 14th divided by 6.2 times 10 to the minus 10th. We get a Kb of 1.6 times 10 to the negative 5th. That's it. All you need is a starting concentration. You can calculate the pH. So let's try one. Here's the kind of question you could expect me to ask. So let's try one. What's the pH of a 0.5 molar potassium cyanide solution? All right, let's say we're starting this one from scratch. We know that KCN is going to dissociate into K plus and CN minus. This is complete dissociation. It's not a precipitate, and we're assuming complete solubility. And we know that positive ions like this, like sodium, like lithium, they don't do anything to affect pH. They have no other function. They are completely inert. But this is the conjugate acid of an acid. If I have a salt like this, a negative ion salt, the negative ion of a salt, I just look for something that looks familiar in our table of acids, and we find that it is the conjugate base of hydrocyanic acid, which has a Ka of 6.2 times 10 to the minus 10th. So the Kb is going to be the exact opposite, Kw divided by Ka, which in this case, Kw 1 times 10 to the minus 14th, Ka 6.2 times 10 to the minus 10th. We get a Kb of 1.6 times 10 to the negative 5th. So what's our pH? We know that when Cn minus acts as a base in solution, in other words, reacting with water, it's going to swipe that H plus off of water and leave OH minus. And so that is what bases do. They produce OH minus by accepting a proton. So our Kb, which we know is 1.6 times 10 to the negative 5th, is equal to concentration of HCN and OH minus, which are going to be equal. And since this is 1.6 times 10 to the negative 5th, it's a safe assumption that we can approximate, but we'll do our little test anyway. So that's going to be our concentration of Cn minus, which is what it was when we put it in solution, because this stuff completely dissociates. So I'm going to calculate H plus, and then we'll do our test, or OH minus, make sure that this works, and then we'll get pH. So I'm going to say 1.6 times 0.5. Remember that these are both going to be x, so this is going to be x squared over 0.5 molar. So if I take 1.6 times 10 to the negative 5th and multiply it by 0.5, I get 8 times 10 to the negative 6th. So I have 8 times 10 to the negative 6 equals x squared. X, which is OH minus, is 0.028. 0.028, excuse me. Now, does this approximation work? We'll just test by dividing it by the original concentration. So that divided by 0.5 times 100 is 0.57% dissociated, so approximation works. So we have OH minus, we know it equals 0.0028 molar. What's pH? You got a couple options. I'm going to take pOH, I'm going to say this is equal to negative log of the OH minus 0.0028. A little neater. 0.0028. So I'm going to take negative log of 0.0028. Hang on. Negative log of 0.0028. We get 2.55 is our pOH. And then to find pH, we simply subtract that from 14 minus pOH. And 14 minus this answer, and we get a pH of 11.45. And that makes perfect sense because it's a base, so the pH should be greater than 7. Now, what if we run into a situation like this? Hang on, let me get one. Here's a question that can come up, and this is where things might get a little weird, but it's just an extra step or two. What's the pH of a solution of 0.5 molar solution of ammonium fluoride? We're going to assume complete dissociation, and we know that this is going to dissociate into NH4 plus and F minus. Problem is that this is the conjugate base. I'm sorry, this is the conjugate acid of NH3. You can find that right here in our table of bases, and it tells you that ammonia has a Kb of 1.8 times 10 to the negative 5th. Also, we know that F minus is the conjugate base of HF. Well, what's this going to do then? You got conjugate acid, you got conjugate base. The way we solve for one of these is we say, okay, which is stronger? Which is larger? Ka or Kb? And whichever one is larger, that dictates how this salt is going to act. So what I'm going to do is I'm going to find the Ka of our conjugate acid. And so since this is the conjugate base of NH3, and we know that NH3, let's go up here and find it. I think it's 1.8 times 10 to the negative fifth. Right here. 1.8 times 10 to the negative fifth. That's our Kb. So let's plug that in and we'll find our Ka. Ka is going to be equal to Kw divided by Kb. We know Kw is 1 times 10 to the minus 14th. Kb is 1.8 times 10 to the negative fifth. So what's our Ka for this particular salt? 1 times 10 to the negative 14th divided by 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative fifth. We get 5.56 times 10 to the negative 10th. Honestly, kind of wimpy. What's the Kb of our conjugate base? So we know that F minus is the conjugate base of HF. Let's go up and find its Ka so we can find what the Kb would be. It says here that for hydrofluoric acid, right here, it's got a Ka 7.2 times 10 to the negative 4. So let's plug that in down here. All right, what's our Kb? 1 times 10 to the minus 14th divided by 7.2 times 10 to the negative 4. So 1 times 10 to the negative 14th divided by 7.2 times 10 to the negative 4. 1.38 times 10 to the minus 11th. It's a close one, but this one is slightly bigger. So because the Ka is slightly bigger, no matter how big, just as long as it's slightly bigger than Kb, this acts like an acid. And how are we going to find the pH? Just plug it in. You know the initial concentration, 0.5 molar. We know it's going to act like an acid. That means that NH4 plus is going to act like an acid by donating this H plus to water to make H3O plus and NH3. So what are we going to do? Let's just plug this in. We know this Ka, we said, was 5.56 times 10 to the minus 10th. And our products will be H3O plus and NH3 on the top, on the bottom, and H4. This is so small, we're not going to worry about approximation. So these are both going to be X. And we'll put in 0.5 molar. And let's solve for X. So 5.56 times 10 to the minus 10th times 0.5. We get 2.78 times 10 to the minus 10th equals X squared. X, which is going to be H plus, and NH3 is going to be 1.67 times 10 to the negative fifth. So we're going to find pH by saying pH is equal to negative log of H plus 1.67 times 10 to the minus fifth. And we get a pH of 4.78, which makes sense. It's an acid, so its pH should be less than 7. Now, some of you are going to say, well, Mr. O, if we put this acid, this salt in solution, isn't it going to make a bunch of NH3 and that's going to act like a base? That's for another time. So we're going to stop here. Best of luck.